Okay, so this is part 2 of integrating. Make sure that you have watched part 1 because you need to have the kinetic analysis part that we're doing. And we're going to integrate and also ultimately the ground reaction force curve. We're going to use the ground reaction force curve to determine position, velocity, and acceleration of the center mass of the person. So let's start out with our plots. We're going to start with ground reaction force on the bottom graph. This would be in the z direction, and this is going to be time. Right above that, I'm going to put acceleration. This would be vertical acceleration, because we're only going to be dealing with the vertical dimension right now. Right above that, I'll put velocity. Time. And then right above that, I'll put position. Now remember, I'll always leave room for positive and negative velocities and acceleration. Oops, 0, that's negative. But position I'll just do from, into the vertical sense, this would be ground level, and this would be something higher than ground level. Okay, we're doing a counter movement jump. I expect you all are familiar with a counter movement jump ground reaction force profile, and I'll draw it quickly, just like this. It's a very characteristic curve for ground reaction force during a counter movement jump. All right, so now we want to integrate it. We know integration means calculating the area under the curve. Well, we're not actually going to calculate the area under this curve. We're going to use this curve to generate acceleration, and then we're going to integrate the acceleration profile to get velocity, and then integrate velocity to get position. Now, let's look at our kinetic analysis equation. Sum of the forces equals MACOM, center of mass. We have ground reaction force minus the force due to gravity equals MACOM. And we know that force due to gravity is body weight. The person is standing on the force platform. In this case, both feet are on the force platform. So this line represents the magnitude of body weight, or FG. Okay, that's a constant. So we know what that is. That's the person's body weight. And then we have some forces under body weight. We have some forces over body weight. Remember, the ground reaction force is not equal and opposite to the force due to gravity. But now what we want to do is rewrite this equation so that we're solving for the acceleration of the center mass. So I'm going to do that right here. A equals FGRF minus FG divided by mass. That's our equation. So what we're going to do, we're going to take, and this is ground reaction force right here. We're going to take every data point on our ground reaction force profile, subtract out body weight, and divide by mass. Okay, that's what we're going to do. Every data point. So right here, this ground reaction force is equal to body weight. So FGRF minus body weight is 0 divided by mass. That's going to be 0. That's going to be a 0 acceleration. This ground reaction force is less than body weight. Ground reaction force minus body weight, which is going to be a greater number for this point, divided by mass. That's going to be a negative acceleration. This point is greater than body weight. Ground reaction force, a bigger number than body weight. That's going to be a positive numerator divided by m. Acceleration is going to be positive. In fact, if we go through this entire process with our math, we will get an acceleration profile that will look just like our ground reaction force profile, shifted just a bit because it's divided by mass. Okay, just like that. And then we're off into the air at that point. So I'm trying to line up this point here and this point here. These are the same points in time. Okay. And these two curves should really reflect each other because that's a constant, that's a constant. So acceleration will vary, however ground reaction force is going to vary. So now we have our acceleration profile. Now we can integrate our acceleration profile to generate our velocity profile. So remember, from the previous, for part one, we would calculate the area under this curve, or the area between the curve and zero, and the area under this curve, the area between the curve and zero, and then this little area here too. How do we do that when it's a curve? Well, remember, in our force platform, we typically collect data at 1/1000th of a second. So I have lots of little data points in here. And so what I really have are a bunch of rectangles. I'm going to draw the rectangles in here. And now you'll see what I was referring to in the last presentation, that we're going to actually miss representing a curve, because see how that corner of the rectangle is off the line? That's an error in our calculation. But if I make my time period really small, like 1/1000th of a second, that error is going to be really small. Or I could shift to using a different type of shape. I could use a trapezoid, which has a slanted side, a slanted top. Okay, and you see how that matches a little bit more. Either is fine, and what you often need to do is determine which shape you want to use when you're integrating a curve. That decision is very much influenced by the sample rate. If my sample rate is really low, I want to make sure to pick the best shape possible to follow along the data set. If my sample rate is really high, in essence what I have are these vertical lots of rectangles which just sit right next to each other, and you can't even tell that there's anything missing on the curve. Okay, so the width of that marker ends up being, for example, 1/1000th of a second, and now you can see it. I'm exaggerating the width here, okay, of our delta t. But now what I'm going to do is I'm going to integrate, calculate the area in that rectangle. That's A times delta t. That's the area in this rectangle. What that is going to represent is the delta velocity, the change in velocity for that period of time. Why do I know that? Because I know A is equal to delta V over delta T. That's my base equation here. I use that, I'm rearranging, I'm moving delta T over here, and now A delta T equals delta V. That area in that rectangle right here is going to represent the change in velocity for that time period. Now, if I know the change in velocity in the previous time period, I can then build on that with the area under this curve. And so and this is part of part one, really what I want is VF minus VI equals A delta T as my main equation, okay? This is the equation I'm going to use, and then I'm actually going to rewrite it one more time, and I'm going to solve for VF, where VI is always the velocity at the beginning of the time period that I'm interested in, and VF is the velocity at the end of the time period I'm looking at. And then when I go to the next rectangle, that VF becomes the VI. And then there's a new VF that I solve for. And so then what I'm doing is I'm building on the data points as I calculate the areas going forward in time. The trick with integrating is I need to know some velocity somewhere in here in order to start the integrating process. If I don't, I actually end up with two unknowns, VF and VI. So I need one of these to be known at some moment in time within this movement. It could be any, maybe I know this velocity at this moment in time. That's fine. I can do the math from there. All right. But typically we don't know the velocity once the person's moving. What's nice is to give the person instructions to be standing still prior to the start of the movement. And if they're standing still prior to the start of the movement, their your initial velocity is 0. So for that very first rectangle, that VI is 0, and now I can solve for VF. Then that VF becomes the VI for the next time period, and so forth. Now we've started that integrating process. But you need to know the very first velocity is 0. Now, what we're going to see in our programming, when we're actually processing data, we'll actually see some error in our integration. A lot of times that error comes from the problem that the person is not standing still at the moment that we want them to be standing still. And if they're moving and we don't know that initial velocity, then our calculations of area and the influence of that on velocity is going to change. Because if I don't know this, then I have two unknowns and I can't solve for it. If I put in erroneously a 0 here when it's not 0, then I'm actually going to have an error in my final velocity. So this becomes a source of problem when you're integrating. And this is why when you're collecting data from a movement where you know you're going to be integrating at some point, you really want to give your subject good instructions and make sure that they follow those instructions. Because if they don't, and the person's moving at the moment you think it should be 0, all your calculations are going to be off, and you're going to have a mess of a data set to work with. Okay, but now we can continue on up here. These are all negative products on this side here. These are all positive products over here. So this is 0 velocity. So I gotta draw these up here. We're going to have some speeding up moving downwards, and then we're going to have some slowing down moving downwards, and then ultimately we're going to be passing through 0 right here. And I've got another video on this PVA of a counter moving jump. And then we're going to be speeding up moving upwards, and then right before takeoff we slow down before takeoff, and then velocity is constantly decreasing, or excuse me, constantly slowing down, moving upwards at a rate of -9.8 meters per second squared. Speeding up, moving downwards, slowing down, moving downwards, speeding up, moving upwards. And then this last period right here is this period right here, which is this period right here in the ground reaction force profile. Okay, and then we can then integrate the velocity plot the same way, calculating all these rectangles. And then we just need to know the very first position point. And then we're able to do the same process here of to determine position data. So we end up with the area under here is V times delta T equals delta S, where this is SF minus SI. So same equation as down here. And then we rewrite this equation to solve for SF. We just need to know an initial position. So the good thing is, because we know we're going to stop with this plot, sometimes what we'll do is we'll say the initial position is 0, but then I'm going to have some negative positions if the person moves below that starting point, and then I'll have some positive positions as well. A lot of times for jumping, I estimate the start point to be the height of the center mass above ground. And then I end up with a plot that will show some downward movement, some upward movement, and then there's takeoff, and then the person's off into the air. Okay. Again, I've got a more detailed presentation on the PVA of a counter moving jump, so you might want to check that out. So let's look at the steps, because now we got to go to, we're going to go to Excel, and then we're going to go to Matlab to do the processing. We collect ground reaction force data. We adjust ground reaction force to solve for acceleration. We get the acceleration versus time profile. We then integrate the acceleration versus time profile, knowing the very first velocity is 0. We're then able to build on the integration of the curve and generate a velocity plot. And then we can integrate the velocity versus time profile to get the position versus time using a very similar equation, but now it's V delta T, V, height of the rectangle, delta T, the width of the rectangle, and then that's going to tell us the change in position for this time period. As long as we know the initial position, we can build on that change in delta S with each interval. Okay, next step is to go to some processing. So next, part 3 will be on using Excel and Matlab to process data to do this integration. All right, thanks.